Hi, everybody, and welcome to this week's edition of Office Hours for AWS. Today, we're going to be talking about building large Kubernetes clusters. If you haven't joined our sessions before, we run these every Thursday at noon to 1 Pacific Standard. And you can come and basically join in on the chat. We'll be answering questions. I have two developers from our Elastic Container Service for Kubernetes, EKS team, here to help answer some questions. So please write those in and we'll get them answered. Otherwise, we're going to get started. Introducing Gyuho.
Hello, my name is Gyuho, and then right now I'm working on EKS. Also on the open source side, I'm working on the project called SCD, and then we use SCD for EKS and to store the metadata from the EKS cluster.
Cool. And Shyam?
Hey guys, I'm Shyam. I am a software developer with the EKS team. So I'm also involved with the open source project. I've been working on Kubernetes for a little more than 2.5 years, and I focus on scalability and performance of Kubernetes. And I'm one of the chairs for SIG Scalability.
Okay. So what is a SIG? You just said that. What does that stand for? What does that actually mean?
So SIG stands for Special Interest Group. In the open source Kubernetes project, we have this concept of special interest groups. So these are dedicated effort groups which focus on a particular area of the project. For instance, I'm from SIG Scalability. We have like SIGs for networking, storage, API machinery, and a bunch of these. So the purpose of this division is to have like more focused efforts and have specialization around different areas.
Okay. All right. And so that helps it so that the community can kind of get around this massive project and have different verticals so that not everybody has to know everything? Is that
Right,
that's
exactly.
What we're getting
Yeah.
at? Okay.
That's pretty much so.
And so you're the SIG chair for scalability.
Right.
So what does the scalability SIG do in general?
So the scalability SIG, it's actually one of the oldest SIGs, or probably the oldest SIG, the SIG which started first. It focuses around performance of the Kubernetes control plane in general, and also being able to scale really large, so to large clusters or to large number of services or large number of ingresses, or have a high pod density. So it's really about pushing the system to its bounds and being able to stretch a lot on different dimensions of the system.
Okay. All right. So does that extend into things like auto scaling as well, or is it really focused on just how the cluster scales in general?
Oh, I really love you bring this up. So auto scaling quite often is confused with SIG scalability, probably because both of them have scale in it, but they're actually kind of pretty different problems. So auto scaling is about dynamically adjusting to the load in the system, like scaling your control plane up and down based on the load you have. While scalability is actually about like the real absolute hard bounds and pushing that. So often, like because of performance bottlenecks or like general architectural flaws or stuff like this, we're limited on certain bounds, and we want to like push it further. Like given enough resources, how big clusters are we able to create, or how many services are we able to create, and stuff like this.
Wow. Okay. So can you talk about some of the things that have actually been done? Like what is the largest cluster that we've seen from SIG scalability side of things? Maybe the beginnings of time and like where we are now. How does that translate?
Sure. So scalability is like a really long, like old effort. Like it's like I said before. We currently support 5,000 node clusters, and that's the biggest scale of clusters that we test for even in upstream. And we continuously ensure that every release scales to at least 5,000 nodes. So these tests are part of the release process and the release validation process. I think it was about 2 years ago in release 1.6, Kubernetes minor version 1.6. It was in KubeCon Berlin that we actually officially announced that Kubernetes scales to 5,000 nodes. Before that, it's a pretty interesting story. Back when Kubernetes started, I think it was released 1.0 or somewhere around that. We just scaled to like, I don't know, a few tens or like 100 node clusters. And that was like at that point, obviously that's like a very big blocker for enterprise adoption or even like regular production usage of Kubernetes. So we identified that, well, back then I wasn't on the project. This is like about, the thing I'm talking about is like 4 years ago. But yeah, that's when we started the SIG and we had quarterly goals to increase the scale of Kubernetes. So it was like 100 and 500, 2000, 5000. So it was a gradual process. It took a while. We made a lot of interesting improvements. A lot of them are contributed by SIG Scalability. And yeah, and over a span of few releases, we could go to 5,000 nodes.
So back in the day then, when all this was going on, the way that you thought about Kubernetes was really different. If you were running Kubernetes, maybe you were thinking about it from the perspective of you might run many clusters instead of running a single large cluster because it just couldn't handle that scale. And so now is that motion changing? Are we seeing more people that really want to have large clusters?
Yeah, so even more than like thinking about large clusters or like multiple small clusters, I think back then it was like still about the project to mature to actually take any enterprise adoption as well, or like just to be used in production. Because people will have questions like, if it's scaling to 100 nodes, only 100 nodes, like does it actually make sense to move to Kubernetes? Because what if I have to go over it and then I'm blocked? I have to like redesign another solution or use some other technology. So it was at that point more about actually making it production ready.
Yeah.
But this question I think is much more relevant right now. As we actually scale to large clusters, this is being asked at a lot of places. Like even in KubeCons, we receive these questions from a lot of folks. If they should be using one large cluster or like multiple small clusters. And yeah, the answer here is like, it's kind of blurry and it depends on what kind of usage you have, and like there are some scalability or some dimensions of Kubernetes right now which still don't scale so well with the number of nodes. We're trying to fix those, and we made a lot of interesting improvements in recent few releases. But yeah, so multiple small clusters still seems like an option for those who are not able to scale to one big cluster.
Okay. And so when you think about scaling a cluster, we've been talking kind of more structured around nodes. Yeah. How does that translate into things like pods as well? And for those of you who don't know, pods are a grouping of containers all put together into a single application package.
Yeah. So yeah, that's an interesting point you brought up. So Kubernetes is not just about, Kubernetes scalability is not just about the number of nodes or the size of the cluster. So like I was saying earlier, there are a lot of different dimensions, and scalability is really a multi-dimensional problem. We have had some recent discussions around these as well, like in our SIG meetings and in KubeCon. So number of nodes is just one dimension, and there are many other dimensions that you can scale on. The number of services, the number of namespaces, number of pods you can have per node, or number of pods you can have in total, number of ingresses. If you go about it, there'll be many dimensions, because every feature or like every aspect of the system that you can stretch on kind of ends up being one of the dimensions. So yeah. It's a really multidimensional problem, and we've only recently started seeing this that way and actually try to find out these bounds on different fronts and identify which are the ones which are like most problematic for our users, or bounds that people are asking for us to push further on.
Yeah. Okay. So I was hearing about some changes that we've been making, specifically to things like the node object, and what that was actually the way that we had to change that as we grew up cluster, as we built up clusters, because things were hitting the endpoints too much. Can you talk about that a little bit?
Sure. So this is kind of an old problem. It has been known for a while, but we actually started or we took action only recently when we started seeing this problem for like bigger production clusters. So in Kubernetes, the kubelets are the node daemons, or the node agent that runs on every node and takes care of running the workload on those nodes. So kubelet periodically posts updates to the control plane. It's called heartbeats, just to tell the control plane that it's still alive. it's basically a mechanism to, let's say, if something goes bad with the node, and the control plane will see stopped heartbeats, and then it can like move the workload from that node to a different node. And these heartbeats are like posted every few seconds, something like I think 10 seconds, and this problem gets, well, this is not really a problem for smaller clusters, but as your cluster becomes bigger with let's say 5,000 nodes, and every single node is going to post a heartbeat every 10 seconds, this ends up to be like a large QPS on the control plane. And that is even more aggravated by the fact that these node objects can be really big, because in these node objects, it's basically a protobuf. We also store the volumes and the images that are in use on the node, and that list can be pretty big. So if these node objects are like big, and the nodes post like a new version of this for every heartbeat, the amount of these node revisions grows so big that HCD disk actually fills up.
Oh wow! Okay.
So yeah, HCD fills up, and when that happens, the cluster is pretty much frozen from doing any more write requests, because there's no more space to do any write transactions on the backend.
Interesting.
So this has turned out to be a problem for some of our larger customers, and yeah, so the SIG Scalability has been working on a solution to fix this. It's already beta by now, and it's already also the default. So what we did was to actually split away the heartbeats from the node objects and just have like really small objects dedicated just for the heartbeat.
Okay. Oh, nice. And abstracting that away, so you don't have massive node objects that you're constantly pushing to. You have smaller objects that you can do.
Exactly.
Okay.
Yeah.
So that reduced the load on etcd then?
Yeah, it reduces the load by a huge amount, like of order of magnitude.
Wow. Okay.
Yeah.
And that helps you a ton over there with etcd. So
Yeah, of course.
yeah, can you talk about the scalability of etcd in general, or and the project and what it is?
Okay, so for those who not familiar with etcd, so at a very high level, etcd is consistent distributed key value store. So we have a very like a simple API, just write, read, and then we also support the transaction. But it is based on the flat key value, like a key space. We don't have any like a directory hierarchy, or we don't have any like a parent or like a child node, like interconnection.
Okay.
So it's just like key value space. So you just write like a full bar, and then you can read from the key value space. And then also under the hood, etcd is like distributed. So we use the raft consensus algorithm to replicate the data across the like a 3 to 5 node. So this is to give Kubernetes control plane the high availability, while we prioritize the consistency. So like we now in the raft consensus algorithm, so it is based quorum based system. So so etcd will continue to work as long as we have like more than 2 like a node available out of 3 node cluster.
Okay.
So you can think of etcd as a like etcd provide one logical cluster view of many physical servers. So that was the etcd, but it's not only used in Kubernetes. It's actually quite popular open source project. So we have a lot of non-Kubernetes use cases.
Cool.
So Uber uses etcd to store their metadata like of their time series database called M3. Also, NTT is Japanese telecommunication company. They use etcd to manage their IoT devices.
Oh wow.
Also, Braintree also uses etcd to power their caching system.
Wow, that's really awesome. Okay, so now in the Kubernetes world and around EKS and all of that stuff, so it helps it's the backend store for Kubernetes. It basically manages all of the state that Shyam's talking about. So how do we, because they're separate projects and it's used for so many different things, how do we keep those concerns together, and how do we make sure that they always work together?
Okay, so I can explain first how etcd is used for Kubernetes. So actually, if you look at the control plane of Kubernetes, etcd is the only stateful component of Kubernetes. So API server is the only component that talks to etcd, and then API server stores all cluster metadata in etcd.
Okay.
So that's how we use etcd. And then in terms of working with Kubernetes and other projects, we try to like make etcd as independent as possible. from any kind of like specific project, but we get like so much feedback from Kubernetes. So we kind of driving the future development based on Kubernetes use case.
Okay.
So one use case I can think of is, so SCD has a lease object. So we have a lease object to keep track of like a time to live. So
Okay.
we Kubernetes use TTL object to have the like a temporary object that expires after time to live.
Oh,
like a
okay.
second.
Interesting.
So
We use that for events.
Oh, really?
Yeah,
Oh,
event.
that's very cool. So
Because
the events
events are-
object in Kubernetes actually uses the etcd lease object.
Yeah,
Yes.
it does.
Oh, wow. That's really
Yeah.
cool. And so it has a TTL on any of those events, and they expire and
Yeah.
just basically are garbage
because
collected?
because these objects are like emitted in huge numbers
Yeah.
that we want to periodically like TTL them out. So
Oh, wow. Okay.
yeah,
I'm going to have to
so
look more into that. I didn't realize that's
Yeah,
how
yeah.
it works under the hood. That's
Yeah.
really cool.
yeah, so we have a like separate storage layer for this, but
Okay.
Kubernetes like has so much of those that like it was hitting the like a scalability limit of like list storage. So one thing we did for this release cycle, we introduced a feature called Lease Checkpoint.
Okay.
So previously, like whenever, so SCD is leader-based system. So whenever leadership election happens, we were refreshing the TTL of those list object back to the back to the original TTL.
Okay.
So, and then for Kubernetes use case, we have more than 5 minute TTL like assigned to each object. Assigned to each list object. But let's say leadership like election happens, and then like the TTL hasn't been expired, and then the previously we just resetting those TTL back to 5 minutes. So like as a result, like those objects like never got to expire.
Oh, interesting.
So right now, what we did to address this issue, we just checkpoint the list TTL onto disk using the Raft consensus algorithm, and then whenever leadership election happens, we just restore from that like a checkpointed like a list like a snapshot file.
Gotcha.
smooth.
Yeah.
Okay, that's really nice.
Yeah. So like basically like a Kubernetes like helping us a lot like to like working on the scalability of SCD database.
Yeah,
Yeah.
that
So-
makes sense.
I just remembered. I don't know if I remember it correctly, but I heard from someone that like etcd implemented the Watch API
Yeah.
for Kubernetes.
Yeah. Yeah.
Because it was like getting expensive to like periodically just.
Oh, so
list-
that wasn't
list
built into etcd before Kubernetes did it?
I think so. I'm not 100%
No.
sure, but maybe.
Yeah, so I was working on SCD since SCD version 2, but
Okay.
right now all Kubernetes using SCD v3 API.
Yep.
So I think what Shyam is talking about, the Watch API semantics in the SCD version 2, where we do not have any like a stream like a call list. So so right now we used to have like a polling like a based Watch API.
Yep.
Like using the HTTP one, but in the SCD v3 we switched it to HTTP 2 based, also gRPC based Watch streaming API. So right now it's not polling based, it's like a pushed like from like a SCD server side.
Gotcha.
So that helps us a lot like to scale the Watch API. And then we do have a Watch API built in SCD, but Kubernetes API server has their own like Watch like a cache layer.
Yeah.
Interesting.
So they do not overload the core SCD like
So
cluster.
So for those people that are on the stream that are new to Kubernetes, can you explain what the Watch API is, or how Kubernetes is architected and how it uses that
Sure.
to basically build itself and be distributed?
Sure. So, Watch is basically a streaming read request. So, the regular read request, which is like just get an object or list a bunch of objects, just does one-off fetching of those objects. But often, for instance, a lot of controllers that are running continuously on the control plane, they need to continuously monitor a set of resources. So let's say a replication controller, whose job is to keep making sure that the number of replicas or the number of pods that should exist for a given replication controller is like matching a given number. So it has to continuously keep watching for the current state of the system. Let's say if some pod dies or some pod is deleted or some new pod is created, it has to reconcile the state. So this is one of the primary use cases to actually create a streaming read request, which is basically an open HTTP connection where you just say watch for these set of objects instead of list for these objects. So you basically initially get a list of all the objects that you've asked for, and then you're sent the diffs, like the deltas. Whenever a particular object changes, you get an event saying that this object changed. So this is an open connection delivering changes to the set of objects, and that makes that improves the design pattern of the control plane a lot, because now a lot of these controls don't need to periodically make the whole list call. Like let's say if they're listing 100,000 objects, then that's a pretty huge amount of stuff to list for. So if you can do that like every 10 seconds, that'll just overload the API server way too much.
Right.
So you want this watch to just watch for those and like only get changes instead of periodically listing for the whole stuff.
Got it. Okay, so that really allows it. So like Gyuho was saying, allows it so that everything could just pretty much subscribe or watch against the control plane, and then or the API server, and etcd's behind it fronting everything or storing all the actual data, and the API server is really the coordination between everything. And so everything doesn't have to connect into etcd itself. Everything can be distributed and can just sit there and get events and then take action on those, do that reconciliation loop.
Yeah.
Very
So
cool.
it's very helpful to have a watch API, because like Kubernetes can keep the data up to date. Also, like technically they can use any database, any other database to do this, but the one thing etcd has is, so etcd implement like MVCC like a storage, which is multi-version concurrency control. So whenever you write the key value store into the etcd, we store all the historical revision.
Oh wow.
So let's say, so Kubernetes is watching on this object, but etcd server goes down, like disconnected from Kubernetes control plane. But Kubernetes API server still stores that like revision, like, which is like a global index, incremental like a global index. So when etcd comes back, Kubernetes can like still like fetch those historical data using that revision.
Oh wow.
So that's
Okay.
something etcd provide to like give you all the like as much data, like
Wow.
and then like never lose the data like in terms of like Kubernetes.
Wow. So as somebody coming from like a relational database, that would be like having a full-on versions table for every single resource that goes into it, and being able to, wow, that's a wild architecture. That's really cool. That makes it really nice for how we build this. So how does etcd as a team that's kind of independently developing make sure that any of those changes constantly are working? Are you integrated with the automated testing that's going on with like say scalability? How does that work?
Yeah, you can.
This is something we pay a lot of attention to in the community, which is like testing closely with the etcd versions. So we have this Kubernetes release cadence of having one release approximately every 3 months, so about 4 releases in a year. And etcd also has its cadence for its releases. And every release in Kubernetes, we are like bumping up the etcd version, because just to pick up some fixes and stuff. And a lot of those fixes and improvements are actually driven by the requirements that Kubernetes has asked from etcd. So it's a closely coupled loop where basically we're asking them for some improvements and stuff, and they're making fixes and improvements, and they cut new releases. We use those new releases as the default etcd version in that particular Kubernetes release, and then we are testing it for the duration of the release, which is like about 3 months. And there's a lot of validation that goes along with it. Scalability testing is like one big component of it. Often we end up catching performance issues with etcd during these scale tests, and we realize, okay, this etcd version has some issue, or okay, this etcd version actually gives a lot of performance improvement. And then we just, if everything looks fine, we cut a new release with the new recommended etcd version. Or often we just end up reverting to the old version if we found some issues and couldn't fix it for the release on time.
Gotcha. Okay. So when we actually release a Kubernetes version, we also say that this is the etcd version that you're supposed to work with. That'll go for that 3-ish month period of that release. That will carry through and will support for another 3 months or 3 releases each. So on and so forth. Okay, going forward. Well, that's really cool. Okay.
So actually, there's one more interesting thing that we developed a framework called KubeMark, which runs simulated clusters. It's kind of a benchmarking framework which runs like load tests against the Kubernetes control plane by just creating hollow nodes.
Okay.
Like you don't actually create a real cluster, like you just create fake nodes which just talk to the control plane and like exert some load on it. And so this is again is something which came out of SIG Scalability. And now it's so much in use that I think HCD also has adopted KubeMark into its own release process.
Oh, wow.
So now HCD, which is like upstream for Kubernetes, now uses.
So there's a lot of cross collaboration between the groups. That's
Right.
fantastic. So it's not like we have to worry that etcd is going to go way over here and we're going to be still stuck on an older version for some reason. That's great. Okay.
Yeah, so whenever we cut a new minor release or major release, we make sure we run those QMark, like a simulated Kubernetes workload against our release branch, and it's for a month to make sure like it doesn't introduce any regression to like Kubernetes. And then SCD is quite a stable project, so we just want to make sure we don't break anything.
Yeah. Very cool. And so in terms of those, so you run those tests for a whole month at a time and just see if anything comes up in that month before you actually cut a real release of it.
Yeah. So like right now, like last time we did, it was all manual process.
Okay.
We just like set up a Prometheus, like a Grafana dashboard against SCD. Also, SCD also has a Prometheus endpoint to expose the like a metrics data.
For those that don't know what Prometheus is, do you want to give them a quick?
Yeah. So Prometheus is like there's a two component Prometheus time series database. Also, SCD uses Prometheus client to expose the like a counter or like any kind of metrics data through the HTTP endpoint.
Gotcha.
So we use that to monitor the SCD cluster while we running the simulated like Kubernetes workload using KubeMark against SCD.
And you're just recording all the metrics that come out of it and
just
evaluating
look at the dashboard, and then if anything like let's say the memory like a spike like more than we expected, then we go inspect the like a SCD process. But like that's the SCD release process.
That's awesome. Okay. And so in terms of, so how does like the roadmap or where etcd's been or is going towards translate to the scalability of it these days?
Okay, sure. So the SCD is quite stable. I don't think we're gonna adding like any like a new major features in the like a near future, but still there's like still like a lot of things we have been doing to improve the reliability and the stability of SCD project.
Okay.
So one thing we did, so we look at the like large scale like Kubernetes cluster like a workload against SCD, and then we found out like the large cluster tend to have a long read transactions, like that involved like large range of like a range request, which is like a read request.
Okay.
Let's say the Kubernetes cluster has like 1,000 part or like 1,000 nodes, and then they want to get like a list of all those nodes. Then it would send like a large range of like read requests to SCD, and then they would create a like long like read transaction. And then if you have a lot of those like read requests, we can have a like a head of line blocking problem issue.
Okay.
So requests keep coming in and they just keep queued up, but SCD is not fast enough to return those like read requests.
Gotcha.
And then in SCD side, we also have a like a write transaction. But like if you have a lot of those at the same time, it can like block each other. And then especially for the like write, we only allowed one write transaction like inside SCD. But if you have a lot of read requests coming in, those read requests like in client side would time out. So and then like previously we didn't have enough concurrency to handle those like large number like read requests. So for this upcoming release, we improved the concurrency in that like a storage layer. So that's one thing we did like based on the feedback from Kubernetes community. And then another feature is called non-voting member. So this is not specific to performance or scalability of SCD, but this is more to help like a community with the operational workload. So SCD for now, each member has to vote for leadership election, and then also each member counted as a membership. So if you have 3 members in the cluster, the quorum size would be 2, and then the cluster size would be 3. But we adding a new type of membership, a new type of member called a non-voting member. So and then so I can get back to the leadership election part. So let's say you have a 3-node cluster, and then all the write requests go through the leader. But if you have a lot of write coming into the leader, but let's say there's some network issue, so network packets are being delayed. So data replication from leader to follower can be slow. In that case, that follower can be slow down and then falling behind the leader. So in that case, it can overload the leader a process, a leader node. But if it, and then they can also trigger the heartbeat timer from the leader node.
Okay.
But what if we have a non-voting member? So non-voting member can join the cluster as a non-voting member, but still that member does not count as a quorum.
Oh, okay.
But then node can still join the cluster, and they're still getting all the data they need.
Okay.
But it won't affect the cluster availability as much.
Okay.
Because the cluster itself doesn't require that as much a quorum number.
So is that so that we
sense.
could? So if you have a non-voting member, does that mean that you could use that to basically pull in all the data and have it all replicated across it?
Yes.
And if something were to happen, you always have that as a backup kind of situation?
Like a hot standby.
Like a
Yeah,
hot
like
standby.
a standby node.
Great.
Yeah, that's the point.
Okay, that's really cool.
Yeah.
All right. What else is on the roadmap for etcd?
Also, we planning to support the downgrade. So I think in operating etcd, even for AWS scale, I feel if you have a fallback or a rollback process for etcd upgrade, is I think it will be very useful for Kubernetes community. But right now, etcd provide all the backward compatibility, and then all the data format is data compatibility. But just to prevent unintended failures during upgrade process, so we trying to in the server side we prevent the etcd downgrade. So basically, you cannot downgrade from etcd 3.3 to down to 3.2. Right now, you cannot do that because right now we think the maintainers just make sure you have to go forward.
Okay.
We're gonna do the bug fixes only for the future release. But right now, a lot of Kubernetes community is still stuck in the old release, let's say 3.1. So we have that use case now. Then now we want to support the rollback process.
Gotcha.
So we're gonna add a new a small flag to allow the etcd downgrade. So whenever upgrade from to newer versions of etcd fails, you can now just safely roll back to the old version.
So would that make it so that we could have Kubernetes you could be testing releases against different versions of etcd almost? You could have your current version running and upgrade to a new version of Kubernetes and set up etcd running the newer version and have that in standby and go, oh wait, there's something wrong with this. We're not ready to actually migrate and be able to downgrade back down to that stable release for Kubernetes.
Yeah.
Fantastic. That's really cool. That'll make a lot more stable clusters and upgrades a lot easier for everybody.
Yeah.
Okay. Cool. And I heard something from the community side of things that there's some multi-tenancy work going on as well, because right now it's a single tenant database, correct?
Yeah. So I don't think this is specific to etcd, but I know a lot of communities working on the multi-tenant Kubernetes control plane.
Oh yeah.
So when we say multi-tenant control plane, they want to have a one Kubernetes cluster, but they want to have some isolation between multiple tenant.
Yep.
Let's say multiple customers. But right now it's kind of hard because Kubernetes there's no network isolation in Kubernetes a networking model. So I think there's some folks from Alibaba, they're working to introduce the concept called networking namespace.
Okay.
But right now, if you just have a multiple a tenant in one Kubernetes control plane, it would break the Kubernetes a service because there's no isolation between. But they want to introduce some a hierarchy in the networking namespace, so they can have a good isolation between namespaces.
Gotcha.
But in SAD side, it's pretty simple because we have a flat key space, and then we also have a feature called namespace. So technically, you can have your own a namespace in SCD,
Okay.
and then have all those isolation between.
So it's a key value store with as well a namespace that you can add on top of that.
Yes.
Okay,
Yeah.
cool. So you could have namespaced keys,
Yeah.
and then you could have multiple namespace keys per customer, for example, in that multi-tenant Kubernetes world.
Yes.
Okay, cool. And does that translate down to the actual physical storage of the keys under the hood as well? It actually separates them. So we have physical isolation as well.
Actually, under the hood, it just wrapper on top of SAD client.
Okay.
So it just add another prefix.
Oh, okay.
In front.
So HCD itself is quite agnostic of the namespaces,
Yep.
but we can program the keys in such a way that we can isolate different namespaces. So different namespaces will have different prefixes for their keys.
Perfect.
Yeah.
That makes
So-
sense. Okay, cool. All right. So going back to Kubernetes and SIG scalability and scalability in general and building large clusters, what are the pain points you actually look for from SIG scalability and what with all of your experience in this space? What are the pain points that you see with Kubernetes and how it scales?
So, let me think of some of the common pain points. One of the things which kind of comes up from time to time is scalability of the networking plane of Kubernetes. So we have a bunch of some scalability limits that we started hitting as we started using really large number of services or really big services. For instance, there is in Kubernetes we use IP tables to actually program the networking layer for service load balancing and service routing on each of the nodes. So IP tables is part of the Linux kernel, and it implements these routing rules. And we've seen performance issues with that when there are a large number of services because IP tables is not super efficient when as you start having thousands of rules in your chains. So with each service there are a bunch of rules that are programmed into IP tables, and if you have a large number of services or really big services, this can be a bottleneck for your network programming.
Okay.
So that's something that has been a little bit of a problem for some really power users who try to use bigger services. But the good thing is we have an alternative to IP tables called IPVS, IP Virtual Server, which is not completely an alternative to IP tables because it does not do it doesn't have some of the functionality that IP tables has. But the bigger part of IP tables where we actually are seeing the scalability issues, which is the service load balancing part. IPVS is an alternative, and it actually stores these rules in a better way. It uses better data structures to actually store this. So instead of a linear list, which is what IP tables uses, IPVS uses hash tables, which is much faster and gives you orders of magnitude higher throughput and really fast packet routing.
Okay.
IPVS is GA in Kubernetes in release 1.11.
Okay.
But it's still not the default. We're testing it out and we're trying to see what are basically waiting for some production usage of IPVS and get some more signal and still go through some bug fixes.
Okay.
But yeah, that seems to be one of the promising alternatives.
And that's a pretty simple change in Kubernetes in terms of at least we've made it pretty simple. It's a couple flags that you pass into the actual control plane and kubelet, right? If I recall correctly. Yeah.
So this is one of the best things about Kubernetes, right? You can have a lot of things extensible and pluggable in Kubernetes. You can just swap out for stuff. So it's pretty much about changing these flags and just use a different.
That's awesome.
Solution.
Yeah, the interfaces that are exposed are so cool that we have all of these different endpoints that we can play with. All right. So what about so when you actually get into large clusters, do you have any scheduling issues? Does things get slow at all, or how does I imagine when you have large numbers of services that your IP tables take a long time to write if you're still using that. What else happens?
Sure, we do have our fair share of scheduling problems, and any big system has to face scheduling problems at some point.
Of course.
And Kubernetes does that as well. So so we've seen a drop in the scheduler throughput and like an increase in the scheduling latencies as you go to larger clusters, like of the orders of thousands of nodes. So for instance, I can talk a little bit about a 5,000 node clusters where we actually run our scale tests. So we are seeing much lesser scheduling throughput on 5,000 node. I think the peak we go is about like 30 pods per second.
Okay.
With some of the parameters tweaked, we are able to achieve till 30 pods per second. Or that was the case of 1 or 2 releases ago. While on really small clusters, it's fast, and it's kind of expectable that this happens because when there are a large number of nodes, scheduler has to go through a larger list of things to evaluate. So it takes more time for it to actually schedule pods, and there's a drop in throughput. But recently we've made some of the there are a bunch of improvements that the SIG scheduling, which is the special interest group that focuses on scheduling, has been making a bunch of improvements, and we've been collaborating with them with scale tests and suggesting some of the improvements from our side. So one of the things which I would consider is like a big change with scheduling is a change in the algorithm, which now allows only to score a subset of nodes instead of evaluating all the nodes. So this is kind of a heuristic. This is used in some of the big systems just to improve scheduling. We don't now go through all the 5,000 nodes for each pod to schedule. We just initially filter some of the nodes. So scheduler has these 2 phases of predicates and priorities. So the first phase, when predicates run, they basically eliminate all the nodes which are unfit for the pod, probably because they don't have enough resources or they have a mismatching affinity with the pod and stuff like that. So once those are filtered, the remaining nodes, which are all like schedulable nodes, are now assigned scores. This is the priority phase, where each of the nodes is assigned a score, and based on the one with the highest score, we just go ahead and assign the pod to that one. So now the change in scheduler now basically takes, once you get like a small percentage of the schedulable nodes, you don't do predicates anymore. You directly go to the priorities phase, and just for that small subset, you evaluate the priorities, and then you assign. So that has given us a bump in the scheduler throughput, and that along with some of the other improvements. So there were some data structure improvements with scheduler, caching and snapshotting. All this together is like now taken us to a throughput of close to 100 pods per second on a 5,000 node cluster.
Wow.
And that's a pretty big number. 100 pods per second on a 5,000 node cluster. Yeah.
Wow. And wow, that's amazing. 100 pods. So in that 5,000 node cluster, how many pods are you actually testing with?
So we test for about 150,000 pods, which is like 30 pods per node.
Wow.
And the scheduling part just goes quite fast.
That's amazing. That's really cool. Okay. Anything else in the like networking space, or anything to do with anything else in the networking space for?
Yeah, there are a lot of things in networking space. So so IP tables was one of the things that I already talked about earlier. That's more like the infrastructure layer below Kubernetes. Now there's also some scalability issues we have seen with the implementation of services and endpoints in Kubernetes. So endpoints is among the different API objects that Kubernetes uses. Endpoints is one of them. Endpoint basically stores a list of all the pod IPs that are below a service. So each service maps to a service endpoint object, and that holds a list of these IPs. And we started seeing issues when we use really big services because they have a lot of pods below it, like let's say 1,000 pods per service. Then this endpoints object is basically 1,000 entries. And because it shows everything in one object as one single list, whenever, let's say, if one pod goes down or one new pod comes up, you have to like change this whole object, which is already pretty big object, and then post it to the backend etcd. So that ends up using a lot of, firstly, quite some space because of these revisions, But the bigger problem is actually that the volume of these endpoints objects that flows through the cluster when, let's say, there's a rolling upgrade of a service, or when a few pods come down or go up, is really huge. So this is quadratic. If you do the math, it's basically as you keep adding more and more pods, the amount of stuff that you're sending to the API server for writes is quadratic, and it's even more than quadratic for reads, because each of the nodes have to now read these. There's the kube proxy, which is the network configuration daemon on the nodes, and that has to like read all these kube proxies. So yeah, that can become a big mess. So again, the good thing is here we are working on fixing this. So there is a design, or it's still being worked on within SIG Scalability, and also we're collaborating with SIG Network to have a new API for the endpoints, so that we can slice this huge list object into like smaller objects and update them so that we can be more efficient.
Is there a cap for that?
Yeah, there is a cap for that. There is a proposal, definitely. I think there's also a cap. Yeah, I'm not 100% sure.
For those of them that are on their stream, would you like to explain what a cap is?
Sure. So KEP stands for, I think, Kubernetes Enhancement Proposal, which basically is the mechanism that the Kubernetes project follows to, let's say, improve something or build new features or release something. It's a fancy word for a design proposal, and it's basically to just like have a well-written proposal which answers a bunch of questions which are needed for everything that we are launching, and then have this reviewed by the community. So every KEP has a bunch of reviewers and approvers, and it has to go through them. And once it's finalized, the KEP is now committed to our enhancement repository, and then we start working on it in that release.
Cool.
So it basically formalizes the release process of features.
And now in the later releases of Kubernetes, we require a KEP for something to actually be put into that release, if I'm not mistaken.
Yeah, I think so.
Yeah.
Unless someone's breaking the process, yeah.
So it's even more formal process so that everybody can actually be able to follow along with how Kubernetes is being developed.
Sure, yeah.
Yeah.
Exactly.
Very cool. Okay, so we talked about networking. What else is on the roadmap for scalability and the SIG, and where's it going? What are the goals? What can we expect in the next year or so as we go through 1.15 and 16 and beyond?
That's pretty... That'll be... so... yeah, that'll have a pretty big answer, and a part of things we haven't yet even figured out yet, but like we have a few things in our immediate roadmap for example, I was talking about this briefly in last KubeCon. So one of the things is we want to improve or rather redesign the pod affinity and anti-affinity features. So these are scheduling features to basically say that please don't mount these pods together, like on the same node, or please do mount these pods together. So these are the affinity and anti-affinity features. So that has shown us some performance issues, and that has been showing us a bunch of issues around performance for a while. And we have a proposal out there, or like rather it's still in the ideation phase, I think, to actually redesign this feature. There is this work around the endpoints API, which still needs to happen, and there's a bunch of things that have to be still planned out for. So we need to come up with this new API, and then have a control plane move over to this API, the endpoints v2 API, and then that's one of the things. And